So this talk will be about the deformations associated with and following mega-earthquakes. And it, as the previous talks, it will deal with the rheology of the asthenosphere mainly, and also of the subduction interface. And this work has been done with various co-authors, postdocs and graduate students, and also it has a lot. This work could not have been done without the data brought by GPS colleagues. And so, what are the data at the basis of this work? You know that between 2004 and 2011, there has been 3 very large earthquakes: the Sumatra earthquake, the Jabat earthquake, and the Chilean earthquake. And these earthquakes have broken a big piece of the subduction interface each time. And what is remarkable, it is that after these earthquakes, the velocities in the plates around have changed by more than 1 centimeter per year at sometimes 2,000 kilometers away from the earthquake. So there has been very huge changes in velocities after the earthquake. So what has this to do with the mechanical properties of the mantle? We can see these earthquakes as natural experiment to probe the mechanical properties of the mantle. When you have a large earthquake occurring, it breaks here the superficial portion of the subduction interface. Now, this motion here induces stresses all over in the mantle over a very large area. And the motions that we see after the earthquake, we can think that those motions are related to relaxation of the stresses induced by the earthquake. And by studying these motions, we will be able to try to understand something about the mechanical properties of all the material affected by those stresses induced by the earthquake. And so, especially the mechanical properties here of the asthenosphere, and also perhaps the mechanical properties here in the lower part of the subduction interface, which is something important for mantle dynamics because plate tectonics is one of the main features of mantle dynamics, and the way plates move with respect to the other is still not well defined, and one of the most crucial areas is this subduction interface here. What are the mechanical properties here on this subduction interface? So the question that we will try to answer using those motions after the earthquake is there a low viscosity asthenosphere? What is its rheology? Is it a Newtonian creep with a power exponent 1 or a nonlinear creep? What is the thickness of the layer with the low viscosity? And then what occurs below the brittle part of the subduction interface? And this problem is not at all a new problem. Elsasser first introduced this problem in the 60s, and there has been many papers since then, including a nice paper by Politz and Barbara some 20 years ago. What is new is that after those 3 huge earthquakes, and also because GPS networks have developed considerably during the last 10 years, we have very precise data to measure the deformation after the earthquake. And the other thing which is new, it is that we have the numerical ability to model this problem in 3D in 3D that is taking into account the fact that we have a slab in the mantle, a slab with higher viscosity, and also the fact that we may have heterogeneities on the subduction interface. And so we hope to get then data on the viscosity in the asthenosphere and in the brittle part of the lithosphere. One point that we'll talk about is that, of course, these motions that we see, it's motions over a few years on a scale longer than the attenuation of seismological waves, but it's not a deformation on a very long time like mantle convection. So the rheology that we get, is it a long-term rheology or is it a transient type of rheology? So let us look more closely at the data. The place where the data is certainly the denser, it is Japan. Japan, which is covered with GPS stations. And also you have stations, GPS stations far away, for example, in Russia and in Korea, in China. And you see here the arrows are the perturbation of horizontal velocities between before and after the Tohoku earthquake. The Tohoku earthquake was here. And what you see here for the far field station, it is the whole, in fact, a GPS time series with here the co-seismic jump and then the velocities after, which was different from the velocity before. Here it's always corrected for the velocity before the earthquake. And so you see that you have velocity perturbations far away. Now, from this data, in fact, we can try to look at them more closely to see, to try to understand, for example, how those deformations vary with distance to the trench or to the earthquake. So one can take points further and further away from the trench and plot the raw data. So what you see here, it's almost raw data, just raw data. Just one thing, they have all been non-dimensionalized so that by the co-seismic. Why did I do that? If you have slip continuing here on the plate interface at the same depth as Tohoku earthquake, slip going on, what you should get, it should be a signal independent of the distance to the trench and just showing the amplitude of slip as function of time. First, a big amount of slip at the time of the earthquake, and then slip which continues. What you see here very, very clearly on this graph, it is that the slip non-dimensionalized by the co-seismic slip increases as a function of distance to the trench. Here it is the points the closest to the trench, and here the points the further away from the trench. And this almost raw data shows that the signals that we see cannot be slip which continues at seismogenic depths at the place where the Tohoku earthquake broke the plate interface. It has to be deformation occurring further. And we can again take this graph and plot here on this graph as a function of distance to the trench. We can plot, in fact, the post-seismic deformation, non-dimensionalized by the co-seismic, that is just, if you want, just the eight of all these curves compared to the co-seismic here as function of distance to the trench, and we get this type of curve, and we'll come back to this curve and we'll see what it tells us what it tells us physically. And this was the case for this was the case for Japan. I forgot to tell you also to speak about the vertical velocities. You see that here you have uplift after the earthquake, and there you get subsidence. Now, if we look at the data at other places, for example, in Chile, you can see here the velocities after the Mole earthquake, the Chilean earthquake. Again, perturbations of more than 1 centimeter per year almost through the whole continent. And you can see here the vertical velocities. And you see more or less the same thing as in Japan. You have uplift here in red on the Andes. You have some subsidence closer to the trench. And you have subsidence far away in the continent. And this we observe for each earthquake. We observe that in Thailand after Sumatra earthquake, and we also observe that far away from the Japanese earthquake. So all those earthquakes present post-seismic motions with very common features. And one thing quite remarkable. Now, you remember in the previous graph for Tohoku, there were those post-seismic deformations far away, and far away the curve was leveling off. Now we can take the post-seismic deformations far away from Japan, far away from Sumatra earthquake, far away from Chile, and plot them on the same graph, still non-dimensionalized by the co-seismic deformation. So all what you see here, it's almost raw data. All what has been done, it has been to scale those raw data by the co-seismic deformation so that they're all put to the same co-seismic motion. It's somewhat a way to take into account the difference in the magnitude in the earthquakes, the difference in the distance. But what you see, it is that for whatever the area in the world, all those faraway data more or less plot on the same curve within something like 20 to 30%. That is the physical process which gives rise to those far-field deformations seems to be the same and with the same mechanical properties in the three areas. And this is also something that you can see here on, I would say, almost raw data. And another thing which is important to know, it is that this type of motion lasts for a long time. What you see here, it is the motion in the South American plate before Tohoku earthquake, but it was something like 40 years after the Valdivia earthquake, the big 1960 earthquake, which broke all this part here of the subduction interface. And what you see, it is that 40 years ago, you keep on having big velocity perturbations. So these velocity perturbations, due to an earthquake, last for a very long time. So to summarize what we see, just looking at the velocity perturbations, there are large perturbations of horizontal velocities. And when you plot them as a function of distance to the trench, you get a kind of bell-shaped curve. The motion increases and then it tends to level off at large distances. The curves are similar in various zones of the world. There is subsidence in the far field and uplift on the oceanward side of the volcanic arc. And the velocities persist for several decennies. And to try to understand more precisely what those velocity perturbations are, we do finite element computations. Here is an example of finite element grid used, for example, in the case of Chile. And another grid, we refine the grid, of course, in the area of the earthquake, and we put the possibility to have various areas with different viscosities. Here, finite element mesh here for Japan, and so on. And the first thing to do with those grids, it is to use the coseismic data to invert for the coseismic slip on the interface, because it is this coseismic slip which will induce the stresses in the mantle everywhere. So it is important to do this first inversion. And one does that very simply using the horizontal motion, all the GPS data that we can get, sometimes also INSAR data that we can get after the earthquake. And we get this coseismic motion. And you see, for example, here in the case of Japan, that we can fit quite nicely both the horizontal and the vertical motion. And we did the same thing for the two other earthquakes. And so now we have modeled the earthquake, the slip on the interface. It means that we can model also, that we can know the stresses induced all over in the mantle. And now what we can wonder, it is once that we know those stresses in the mantle, it is what induces the post-seismic motions that we observe. Is it slip on the fault plane, relaxation in the asthenosphere, relaxation in a low viscosity channel? What is the combination of these elements which will give us the best fit to what we observe? And for example, this is the inversion that we did, in fact, for Japan. We took a simple model where we inverted for viscosity here in the asthenosphere in blue, and then we have a pink area here that we will name the low viscosity channel. We can try to have it going further down in the mantle, because this area there is perhaps an area with a lot of water that can be perhaps with a lower viscosity. And also perhaps we can have a low viscosity wedge below the volcanic arc. And the question that we have to answer is, what is the best viscosity to put in those various layers to get the best fit to the observed post-seismic data? And what can we resolve, in fact? And the answer that we get is that we must get a viscosity in the asthenosphere of a few times, here around 2 times 10 to the 18 Pascal second in the asthenosphere. We need to have a viscosity here in this pink area here that is the low viscosity channel, the lower part of the subduction interface, which is quite low, of a few times 10 to the 17 Pascal second. Of course, this will depend upon the thickness of the channel, and in our case, it is 20 kilometers thick, and the exact answer will depend upon this thickness. But you need to have some easy slip in this area once you put a stress perturbation there. And the yellow area here is not well defined. In fact, we can put a viscosity there of the order of a few times 10 to the 17 Pascal second in a low viscosity wedge, but it does not improve very much the results. So I would say it's not very well refined. And in the case of Japan, we do not need explicitly post-seismic slip on the interface at shallow depths, as long as we put a very small component of Berger transient creep in the mantle, as long as we put a small Kelvin void, not only a Maxwell rheology, but a Kelvin void rheology in the asthenosphere. Now, this is the type of fit that we obtain once we put these rheologies. Here you see the predicted and observed horizontal velocities. This is in 2 years after the earthquake in 2012, and the vertical velocities. And here is the fit to the far field stations, which is also rather good. Now, what I would like to I have to hurry up, I guess. 4 minutes. Okay, so what I want to point out, it is that not that the various areas here, the channel, the asthenosphere, all give very different patterns. Varying the viscosities in those various areas yields different patterns of velocity perturbations. For example, here you see the velocity perturbations linked to a velocity perturbation in the low viscosity channel, in the deeper channel, here in the asthenosphere, and that is the same thing for the vertical velocity. For example, you see that lowering the viscosity in the asthenosphere does not make an uplift on the eastern part of Japan, which is what we observe. And in order to get the observed uplift on the eastern part of Japan, you need absolutely to have this low viscosity channel. On the other hand, if you don't have a low viscosity asthenosphere, you will never do the large wavelength velocity. You will never get the large wavelength velocities that you observe at the stations in Russia and in Korea. So you absolutely need the low viscosity channel and the low viscosity in the asthenosphere. And okay, we more or less get the same thing for Chile. Just in Chile, we have very good data close to the coast because the continent arrives close to the trench here. And here we need some extra slip on the subduction plane during the first 2 years after the earthquake. And we get viscosities in the asthenosphere and in the low viscosity channel of the same type as the viscosities obtained for Japan. And again, we obtained more or less the same thing here for Sumatra area. And now, I showed you this curve at the beginning of my talk. This curve shows the dependence of the amplitude of the post-seismic deformation, non-dimensioned by the co-seismic, as function of distance to the trench. What occurs, I put here an asthenosphere with a thickness of 150 or 200 kilometers. If the asthenosphere has a thickness of something like 600 kilometers in the whole upper mantle, these curves continues up in the model, continues up straight like this. So the fact that these curves levels at large distances indicates a zone of low viscosity of a finite thickness, something like 150, 200 kilometers. It's not very precise because at large distances we have large uncertainties of the data, but clearly we need, the zone of low viscosity needs to be of finite thickness. And the other thing that I want to point out is that I also showed that for the various earthquakes, all the curves plot together. And those three earthquakes, the magnitude of those three earthquakes is different by about 0.5. That is, the stresses induced in the mantle differ by a factor 5. Now, if you have a polar law rheology with n equal to 3, a factor 5 in the stresses would be like a factor 25 in the viscosity of the asthenosphere. Now, the displacement of those faraway stations is governed by the viscosity of the asthenosphere. There is no way that you can have a factor 25 between the apparent viscosities after those various earthquakes. So we have no sign here, at least in this process, of polar law creep. Okay, so the summary of the results is that we need relaxation in the asthenosphere necessary for explaining far-field horizontal and vertical velocities. The viscosity has to be of the order of a few times 10 to the 18 Pascal second, and the asthenosphere needs to have a finite thickness. One needs absolutely also relaxation in a low viscosity channel in the lower part of the subduction interface, and this is necessary for explaining, in particular, the uplift on the volcanic arc. And so, this viscosity that we see of the order of a few times 10 to the 18 Pascal second, perhaps this is not a long-term rheology, perhaps it's a transient rheology, the long-term rheology being more of the order of 10 to the 19 Pascal second, and we did some tests using longer-term data, and this could be perfectly compatible with a longer-term rheology of the order of 10 to the 19 Pascal second, this viscosity here being a kind of short-term Berger viscosity. But you expect that because the mantle is not something homogeneous. And when you have a mixture of materials of different viscosities, you expect to have transient creep, and the first viscosity that you see on a short-term time scale, it will be the lower viscosity, in fact. And also, the lower part of the subduction interface really seems to deform easily to have a low viscosity. And there are numerous other implications to this type of study, but more of more tectonic implications. For example, the stresses in the plates don't seem at all to be something steady. And personally, I'm not sure at all that the deformations that we observe nowadays during the last 20 or 30 years with GPS at the millimeters per year, of the order of a few millimeters per year, are all long, significant on a million-year time scale. Well, thank you for your attention, and thank you for also the organizers of this symposium.